Okay, hello everyone. Welcome back to Turing Complete. Last time where we left off, I was having a really hard time with the counting signals level because it requires that you have a signal counter in the output. So if we go back to Turing Complete here, we go to, yes, counting signals. The difficulty is that it requires a signal counter, and that's pretty difficult to implement without knowing how to add binary. That's my assumption. They did teach us the half adder. So we have some element of binary addition, but nothing fleshed out enough to the point where I feel like we could just jump into a signal counter. So what I want to do is I'm going to leave this here for now and keep going. So I'm going to go into the full adder, and hopefully we'll have more better retroactive knowledge to go back. So this music is getting a little loud for me. I think it's just the song, really. Okay. I also wanted to clarify what the comparator does. So last episode I spent probably the greater part of an hour figuring out what a comparator did. And I didn't quite figure it out. The premise, I had the idea, but there were some unique characteristics and quirks of a comparator that I didn't cover. So here's a comparator. I should actually go back to this gate, the XOR. As you see, this was my first design of the XOR, then we reduced it again after we figured out, we redesigned the XNOR and then inverted it. And then there's this design. And I took this design from a channel called Matt Batwings. So this design for an XOR gate actually illustrates a comparator quite well, specifically its subtract mode. So right now, as we touched on the previous episode, there's two modes in the comparator. There's the compare mode and the subtract mode, or it might be subtraction mode. So if we go to the truth table in XOR, just as a refresher, an XOR is an exclusive OR gate, meaning that it can be, if one of the inputs is on, then the output is on, but not both. In other words, if both states are the same on the input, the output is off. So if they match, then there's no output. But if they differ, meaning is only one of them is on, it makes an output. So, okay, if we go head over here, let me just turn up my brightness ever so slightly. One moment, guys. Great. And then we'll check on the stream health. Looks okay to me. Get back to the game. All right, so as we know, if we power redstone dust, it goes for the power starts to decay immediately. So if we have a lever, excuse me, stumbling over my words today, we can visualize, or it visualizes this decay. So you have the brightest dust here, and then as you can see, it gets ever so slightly more dim as it goes. And this trend will continue until you hit block 15. Or I should say block 16. So here's the weakest part of the signal, and then the strongest. If we take a lamp, and we put that just after where the signal fizzles out, there is no output. But if we do it right at the end, where there's still a signal, it powers the load. So if we go back, so we can gather that from the source, it can go 15 blocks before it goes out completely at the 16th block. So we have a lever, and then we have a dust here, and then we have our comparators, so what they're powering. So this is a pretty clever XOR gate, so I'll just illustrate that it works. So obviously when the state's the same, i.e. both inputs are off, the output's off. If one of them is on, the output is on, but not both. See how that works? So a comparator compares signals. It's in the name. So if we have a signal strength of 15 here, right? And this is on. This naturally goes to 14, and so does this, okay? So that means that the strength, the signal strength going into the side of the comparator is the same as what's going behind, which is capable of powering this dust. Why? It's going through this block and powering this dust. Why is that? So a comparator in subtraction mode, if the side dust is a greater value than what's behind it, so let's see here. How do we? See, this is what happens when you don't prepare your presentation. Trying, guys. Okay. So what do we have? Okay, so that illustrates it. If the signal strength going into the side of the comparator is greater than that coming into the back of it, it will not produce an output. Okay, so that's powered. If we release it, it starts to power. If it is the same, also true. Right. If it is the same, then it refuses to power. But if the back is stronger than the side, then the power goes through. So how this works is a bit of a rough explanation, but how this works is they're both in subtract mode. And then when one of these is on, okay, the power coming from the back of one of these comparators, of this comparator specifically. So we're at 15, 14, 13. 13 is going into here. 12, 11. The signal strength on the side is weaker than that coming from the back, and power goes through. It's the same on this side. So we could just ignore how this is all wired up. This isn't actually producing an output, as can be, well, that's being powered, so. See, not producing an output. But if you have both on, now the signal strength is equivalent, and therefore nothing is powering. So if we go here, 15, 14, 15, 14, they're equivalent. Same case over here, 15, 14 in the back, 15, 14 through the side, no power. You can see how that works. It's a pretty clever design. I don't know if Matt Batwings actually conceived it, but this is going to be our central design going forward, because obviously this is, one, not easily memorizable, and two, a bit bulky. This is pretty compact, more compact, takes less parts, and I've already memorized it, which is super nice to just not have to go back and refer or do any cloning. So we're gonna move on using that. I've taken the liberty of redesigning the odd number of signals level, where if you recall, if there's an odd number of inputs, then the output is true. See that? That was 2 is off and then 1 is on. So check out this. This is a lot more compact. And I told you guys I wouldn't use repeaters, but here we are. We're using repeaters. That's more symptomatic of the design here, is that the output is kind of variant. So it's either 2 or 1, which is a bit strange. So what Matt Batwings does is he just puts a repeater there so that it sort of equalizes it all, if that makes sense. So it's either off or on. So that feeds into another XOR. Obviously, we just have 3 XORs, and they're changed into 2 XORs. They're changed into 1 final. And I'll just demonstrate. So everything off, output's off. Odd number of inputs, even number of inputs. Odd number of inputs, even number of inputs. See how that works? And that goes true for every combination. So that's a lot easier to understand and visualize. So I also took the liberty of redesigning the half adder. So here was my design, and then here is the new design with Matt Batwings' XOR gate. So, you know, it's not like amazing. It's not like significantly smaller, if you could check this out, but it's a lot better. So as you can see, this serves a bit like, yeah, this is essentially just a standard XOR, and then you add an AND that's connected to both of these switches. So we're just illustrating binary addition. So if we add 1, there's a 1 and a 0. If we illustrate or equivocate these inputs to 1s and 0s, so 1 on meaning 1 and off meaning 0, we could do binary addition. So I'm going to go ahead and let's find like 2 good blocks to do this. Let's say that red is on and black is off. Okay? Or no, I'm sorry. Yellow or green should work a lot better. So we'll do green. So here's our board. Okay. We're going to add some binary. Right? So the sum is obviously the total when you add up numbers together. When you add numbers together, you get a sum. The car, or carry in this case, is the carryover. So in the standard, tens based number system that we use in school, whenever you exceed 9 when you're performing addition, you have 10 and then you have to carry the 1. I'm sure you're familiar with that. But it's the same goes for the twos system, I suppose you can call it. I think it might be called the twos complement. I'm honestly not sure. Same goes for the twos. So let's say this is our sum. Okay, so it's all black, meaning there's nothing on the board. If we did, okay, actually we'll do this because we're adding 2 values. If we did a 1 plus 0, obviously that's 1, right? So there's a 1, great. If we did 0 plus 0, that's a 0. But what happens if we do 1 plus 1? So obviously we can't exceed 1. Now we're hitting 2, which doesn't actually exist in binary. It's a 2 system. There's only 2 possibilities. So what do? So we can mark that as 0. It essentially becomes, you just instantly carry that 1. So then we carry it over the top, okay, like in standard addition. And then 1 plus 0 plus 0 is 1. So what this actually turns out to be is if we have 1, 0, 0, 1, starting from the right, and we head over to our little byte over here, it should help us. So that would be, I should actually remember what we added together. So we added 1, 0, 1, 0, and 0, 0, 1, 0. So 1, 0, 1, 0 is 5, and 0, 0, 1, 0 is 4. So we did 5 plus 4. So then the sum was, we did 5 plus 4, correct? Yeah. The sum is 1, 0, 0, 1, which would be 1 plus 8, which makes 9, right? So again, we added 5, 4 plus 1, and 4 to make 9. See how that works? So from the right, you count it, what these, in a byte, what this represents is the values 1, 2, 4, 8, 16, 32, 64, 128. It's taking the power of 2 because it's a 2 system. So it takes the power of 2 of every value, and it keeps moving to the left as the place gets moved. This is a very rough explanation, but I just wanted to quickly go over that before we moved on to the full adder. So what this logic illustrates is the carry function, that what we did right there. So if we have our sum, 1 plus 0 is 1, right? That's on. 0 plus 0 is 0. 1 plus 0 is 1. But if we have 2 1s, it drops to a 0 at the bottom, and then the carry is now a 1. So that kind of stops us right at the carry. We can't do anything because from there. That's why this is called a half adder. So my understanding of what a full adder is it allows us to actually do these binary computations. And that could be totally wrong, full adder. So let's go ahead and head into Turing Complete. And we could see the XOR and the AND. Same thing as Minecraft. I have an XOR and an AND. And we'll illustrate. So if one is, it's basically just an XOR. Glorified XOR, and the carry is just an AND gate, right? So 1 plus 0 is 1. That's the sum. 0 plus 1 is 1. That's the sum. But 1 plus 1 is sum of 0. And you carry over the 1 because you can't exceed 1. You can't have a value of 2. So All right, let's move on. So that was the half adder. So we're going to do the full adder, which I have never implemented. So this is going to be just as new to me as it is to you guys. On the previous, or sorry, in the previous level, we added together 2 inputs, correct? This time we add 3. Okay. Once again, add the inputs together in binaries such that the result is either 0 or 1. As with normal addition, if the result cannot be described with 1 digit, as in like it cannot achieve 2, like we explained earlier, set the carry to 1. Okay. I feel like this just feels like 2 half adders together, if I'm not mistaken, and then you connect the carry with some sort of like XOR gate, right? I could be crazy, but let's try it. So we have our XOR, and then our AND. I think that's probably the cleanest way to do this. If we could just move these around, and what that exceeds like 2 units, so maybe this needs to be up 1 more. Then grab that. And then let's see, that's, what is that? That's roughly, yeah, let's just say like 2, but if it, really strange. Okay. Whoa. Oh yeah, guess what I found out? In Turing Complete, if you select an item and hit spacebar, you can rotate it. Do you know how much more efficient my designs could have been if I just did that? If I knew about that. Oh boy, anyway. All right, so the 3 inputs is a little confusing. So we have our truth table, right? So we have 3 inputs. I guess we just, yeah, let's just go with my theory. Oh, that's terrible. We gotta separate this 1 more, and then 1 more. I mean, if it is true that we're just doing, I'm literally doing 3. I'm doing 3 half adders. I don't know if that actually does anything for us. But this is my intuition speaking. So as far as I'm concerned, it's you connect the both. Oh, right. It's actually, it's actually just 2 because you need 2 inputs per half adder, which totally makes sense. You got to add, you have to add them together. So you're adding the inputs. So if you only have 1 input, that just makes 1 or 0. So I believe it was, you have the first input on 1 input of either gate, and then the same thing with the second. And then I think it's a bit rough, but this one is going to be a little bit special. This is a special kid right here. He's in charge of 2. And then let's add this. Okay. So next one, an AND. I think in Minecraft, we just, that was, yeah, right. So the sum and carry. This is the sum and carry. This is the sum and carry. I mean, let's take a wild guess because XORs are kind of just the gate. I mean, what I mean by that is they just are great for everything. So it's a great little guessing gate. So, okay. We already have a 1. So what got powered there? If it's all 0, oh, I'm sorry, that's an XNOR. That doesn't make any sense. That's been getting us a lot on this stream, is the distinction between XOR and XNOR. So, okay, here we go. True. True. No. Okay. So what went wrong? Seems pretty self-explanatory that this would be the problem. Because I gave him too much to be in charge of. Now he's doing an AND and an XOR. So he's powering the AND, and then therefore that powers the XOR, which would power the sum. So it kind of does come back to our gates. So, or just our guesses. So let's see. Great. The sum is 1, right? Sum is still 1. Then we have our carry, okay? So that's fine and dandy. I mean, if we did this, we're good for X amount of time until we hit this. So now that should go to this input. we're treating this like a truth table, all right, let's stop just guessing. Actually, let's start guessing. So what got us past that half adder level was doing this. And I like how that looks a lot more. Love the wiring there. That's what got us out. Okay. I feel like this should be on an XOR. And then connected here. Am I crazy? And that goes to the sum. So it's good for that long. And then 1 and 3. If it's 1 and 3. Why do I feel like a triple and would be good here? Two, three, four. So this makes a byte. Okay. So you can see why a byte is so standard, is because that's what makes a full adder. Is it's two half adders together, and then now you have a full adder, and that represents, what is that? 1, 2, 4, 8, 16, 32, 64, 128. So the maximum value is 128. So you can represent 255 values, right? I think that's correct. So that makes so much sense why, if you see this in full stack, if you're doing CSS, like, oh, the color values go from 0 to 255. And so there's a very distinct range here. And it boils down to just these few gates. So as long as I could figure this out, this will be cool. The desired carry is 1 right now. So, let's be a little bold. Oh, so now it's all 3 is required? I thought an and was at least 2. Okay. Well, that didn't work. Let's go back to that standard and. So obviously we're good till here, and then so 1 and 3 make for a carry. We could just bomb through and just keep doing combinations, but that's just not very effective. So watch, I could just do 1 and 3. Oh wow, and then you take that and give it another XOR, you throw that on there, and you throw it on the carry. So it's like, sure, that got us past. Now we're here, so what does this mean? If 2 and 3, then there should be a carry. But now the sum is 1, isn't it? I keep nuking this, but I just want to really do this right. So level log. We add together 2 inputs. This time we add 3. Once again, add the inputs together in binary such that the result is either 0 or 1. Okay, let's go back to our half adder. I mean, it's really just that. So you have what is this? I didn't visualize it very well on this level. Let's redo this. And if we can't figure it out right now again, that's a good thing, because then we'll really understand how this works. Let's just give it some space so we can see what's going on, you know? So I thought it was this. Is that not what it was? Yeah, that's right. No, I'm just going to be a particular little guy and do that. No, that ruins it. Yeah, no thanks. So we'll go back to this. Get this nice and small. Okay. Now we're back. Let's make our very compact half adder now. I could be starting in the wrong place by assuming that the half adder is so important, but I don't know. Oh, right, because the inputs are not so close together anymore. What were they in that half? Oh, it was one of these doubles. So they were functionally right next to each other. We take this individual. They were really like this. I mean, that's as close as we can get to what they were like. So I like that. I like how that looks. Okay. And then this is where we go wrong because now there should be a sum. I just feel like it only makes sense that there's an XOR. We connect. Let's just try 1. I mean, what do you guys think? I feel like I'm a little crazy here. Wow, wow, look at that. Can you not get it through? That's terrible. Quickly check the chat. Oh, hi, everybody. I'll drop something in the chat. How are y'all doing? I'm just building a computer here. Hope you enjoyed the stream. See, now it immediately goes wrong because that instantly powers an XOR. But so I guess it's an OR then? Now what is wrong here? Our desired sum is 0, but it's 1. Why is the sum 1? Because the OR. That's what I thought we were solving with the XOR. Right? But then it ruins because our current sum is now 0 because it's an XOR. Okay. So this is unique, I have to say. Why is an XNOR effectively an AND gate, but you just throw something on when they're both off? Kind of interesting. So I guess that kind of kills that theory. Okay. What gate could we use to connect these? An XNOR? I mean, what's the gate here? Because we can't connect, but can we? Yeah, I knew. Okay, that's what I thought. Whew. Here, what do we have here? So let's go back in Minecraft. So now we have our carry. That's a different state. Okay. Back in Turing Complete. So now the sum should be 1 because the input is 1. I can't do that because that's a short circuit. So how do we get it? I guess we just go down the line and kind of try 8s, right? So Because I'm having a hard time thinking this through. Now that, see, that just totally nukes it. If we did an XOR, which is what I thought, it does get us there. But now there's a problem here because the desired sum, or the desired carry is 1, but the current carry is 0. I guess that's more of a carry problem then. So I guess we do another AND gate. And then another XOR. Okay, that got us somewhere. So now when input 2 and 3 are on, the carry should be on. Right, so another AND. And then, dare I say another XOR? Okay, so that did it. We have the full adder, which is a really interesting component. Look at that. Adds 3 bits and outputs the sum of the carry. I guess 3 bits is all you need to represent a, well, 3-bit inputs is all you need to have 8 bits of output, which is a byte. Okay. I feel like this could be done better, so bear with me, guys. I'm going to quickly check. They didn't provide a solution. Okay. They did not provide a solution. So what are we doing here? Do we try the bus thing again? So let's just take our inputs. Take that down. Let's try this bus strategy again. Let's give it a lot of leeway. Okay. We have our bus. I feel like this should make it a little better. We'll start our XOR up here. We'll just put our sum and carry like somewhere approximate over here. Okay. That should also be connected to the XOR. Now our AND. We're going to throw our AND down. We're going to give it 1 degree of space. Degree. Shouldn't say degree. 1 unit of space. There's the carry, right? Okay. So now that needs to power. So input 3 needs to give a sum. So we need an XOR. We can do right through there. Look at that. Okay. Now I regret not doing this with our lovely little colored inputs. So if we go back to our behemoth design for counting signals. So what do we have? White, yellow, red. I got my screen tint on, so let's take that off. White, yellow, orange, blue. Great. White, yellow, orange, blue. White, yellow, orange, blue. Oh, I wonder if we could just... I think we could just copy this. Paste it. Excellent. White, yellow, orange, blue. So I know it's a little heartbreaking, but we're going to get rid of this. Now I can't actually see the colors again because they turned it back on. I think this is right. No, it's not. Yeah. I think orange, and we're good. Right, so now we're looking a little better again. Let's go back to white. Yellow. And then I remember we used gray for the last components. Oh, I'm liking that. Look at that. Yeah, that's gorgeous. Love that concision. Check that out. Oh, but you know what? It doesn't even really, it's not really relevant because that's not correct. It doesn't connect to that XOR, so it goes down. So we actually want this up again because you need to, yeah, it's too good to be true, it felt. So, or it didn't feel, it just like, that's, in retrospect, it was too good to be true. Okay, so now this is powering that XOR, and we're gonna get that orange again. I believe it's that. Orange. Gorgeous. 1 and 3, which is gonna take another and. And then I think that's the orange. And that's going to, that's another, yeah, the carry, so. Oh, you know what? We actually wanted that a little lower. As such. Okay. Now we can do this little fun. So look at that. Not too good to be true. Okay. Some things in this life aren't. As in aren't too good to be true. Yeah. 2 and 3. You know, just a quick thing. This has actually helped me with English, which is funny to think about because the double negation law, right? So of course I'm gonna. So let's say we have a not and it's connected to an on. It's inverting, right? So the on is inverted to off. But if you throw another not, then it's just on. It's the same state. It goes the same if you had an off and it's inverting the state. And then so that's on here, but then it inverts it again. So it just ends up being the same as the input. It's the same thing with some English phrases. So if you said it doesn't not exist, if you think about it, doesn't, embedded in doesn't is does, are the words does and not. So it does not exist. You're canceling out those nots with the double negation law, so it does exist. So if you say it doesn't not exist, that means it does exist. But if you're saying it doesn't exist and you have one negation, that means it doesn't exist, it does not exist. Or if you just say it does not exist, same thing. So I just thought that was cool. It kind of helps you think about that. Because I guess I had a hard time thinking about that double negation when it came to language when I was using it. So I didn't understand how to do that dynamically to just understand that. Where are we at? We're at 39 minutes. Great. So let's move on. For all intents and purposes, this might have just been a better looking way of doing the same thing that we did earlier. I mean, wait, how many gates were we at? Yeah, I'm thinking it's going to amount to roughly the same. It just looks better. Okay, so now, so how do we make this with less gates? What, you have input 2 and 3 that give you a carry? Does that connect? Oh, thank God. Oh, but it doesn't because that is dissatisfactory. If we offset this just by a little. We're kind of upsetting the balance here. But I just want to make sure this is clean. Right? I mean, it matters. So now you have your two ands, which are powered here. Oh, it's actually not the white one. It's the yellow one. Yeah. So that's another XOR. So let's make this look pretty. I think that's, if we split the difference, there is no split. So let's say just closer to that XOR, a little farther from the AND. Does that look good? What if we did closer to the AND farther than the XOR? I mean, it looks better in the wire perspective. What if we did this? That, yeah, okay, that's the winner. Money, so. And then all three. Okay, so I think that's less. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Same amount of gates. Okay, we. Yeah, I mean, I feel like that's the most effective way of doing it, though. Am I right? Because you can't connect. It's literally short-circuiting is kind of our problem. Okay, so moving on. This we're gonna settle. That's our full adder. Okay, so we're gonna build this in Minecraft, and if it's not the most effective one, so be it. We'll be okay. Let's give ourselves plenty of room. Okay, and then we will close off the right side accordingly, depending on how big we get this design. So we have 3 inputs, which actually does kind of determine our width. So we need, okay, assume that these are 3 blocks wide each. Okay, well, this is actually 4. That's 4. This is literally 1. That's 1 block wide. So this gets a little funky. 4, 1, 1, 1, that would be 7. So if we add 7, 8, 9, 10. So if I think we can do this in 10 blocks, but if we need to extend the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the XOR has to kind of bleed over this way. Maybe we can try buses with Minecraft. Because that's been our biggest problem. Now I know it doesn't look great, but in order to do buses, we have to do them vertically. Because problem is, you can't really do buses horizontally because you can't lay over. I mean, you could. It's just a little harder. Why don't we, let's go for gold. Let's try to do this. We're ambitious people. Let's try to do this. Try to make horizontal buses. I actually do want to use, I know it's kind of again, I don't want to color code different. Screw it. Let's do it for now because we can always replace the blocks. So yellow, and what was our color? Orange. Okay. Okay. I think they Yeah, this definitely needs to be. So it's just going to be horizontally wider. That's the problem doing buses in Minecraft, is the tileability of this is just difficult. I guess it would be easier to do this if you had one block here, because then you wouldn't have to deal with the repeater problem. I think that's our best bet. Well, you know what you could do? You could do, just to make sure, is yellow the second? Yeah, it is. Wow, my response time is pretty slow. Okay. If you did this, and we took gray concrete. So let's say we have our wire, aka dust, and you can see, oh no, this is all connecting. Not good, right? Not if we use separator blocks, which we designate to gray, which separates all the signals. And we're going to use repeaters because we are not going to restrict ourselves in terms of, signals. So there we go. It is 4 blocks tall. I get it. But this will, I think it'll be 5. Yeah, it'll be 5. Practically 5. Because we can then take signals out this way. Am I right? I mean, so then the inputs will kind of have to come from here, which is, Now we could fix this with one more. No, we can't. That works. That works. No, it doesn't. So how do we fix this? I think we just pull it out one. Right? Okay. I think that's reasonable, and we don't want to delay. You're already running into problems with that. Okay. Here's our bus system, and I'm actually proud of it. I think that works. It's simple, it's cohesive, it's fast. Okay. Now we have our XOR. What color did we, I think it was blue. Yeah, it's blue. Mind you, I can't actually see the blue because of my tint. I'm just guessing that's blue. Yeah, it says blue concrete. So, I mean, how low do we want this? I think you want to split the difference. So for our XOR was this. Okay. See how easy that is to memorize? That's our XOR. And we have 3 ands. Our ands just kind of look like pluses with a hollowed center. It's one way of looking at it. They're just kind of like a wheelbarrow in my head. So look, okay, I guess our little calculation was right. Looks like we're gonna need a little more space. I guess we could try it. So let's just, let's try it. Okay. Because we'll really go test to see how good our busing system is. So XOR needs to be connected to white and yellow. I already like how this is, oh, see? I think we're gonna need to drop this lower. And, you know, we can even be so bold as to slightly, I think it's okay to slightly change the design. Crazy that I'm saying that, but it's slightly okay to change the design of these gates for the sake of redstone cohesion. So if we have our white input, yeah, that works lovely. It's lovely. Okay, we're ripping the repeater because recall, if you have a dust that's powering this block, it can also power the repeater. But this even if it's powered, cannot power the repeater because the repeaters can only take input from the back. So let's give that a nice little test run. Right? Great. That's fine, we'll leave that. And then the yellow. We can rip that signal directly. Okay. You know, I'm actually happy that, man, just in general, but like, I feel like this busing system is really gonna help us. Right? Let's go, let's see. Like, it shows that we're improving. We're getting more formal, more professional from stuff like this, right? We're getting more comprehensible. So white and yellow into the next and. Okay, tell me that isn't gorgeous, right? No, it's not. No, it's not. It's not gorgeous. I think we just rip it directly again. Let's not deal with that. And then white can go low. You know what's nice about these repeaters is I could power this through directly and then drop it. Drop the signal. And then if we used a slab, right. That makes, oh, we got a kid outside. Excuse the background noise. He's very cute. Okay. Yeah, I can't believe that worked. Ah, that's so satisfying. It really is. Oh, we got a little extraneous block there that needs to be cleaned. Let's just prepare these outputs. Oh yeah, right. We can't forget the and has to be knotted at the end, at least in Minecraft. Nope. See, I can't see with the color. Right. Check the stream. Great. Okay. Cool, so we're done there. Next and. White and orange. I don't know why I said that so loud. Okay. White and orange. So I think it's going to be a little easier over white. Ooh, no, because... No. Not that simple. But you know what? You could take the liberty... Oh, you can't. You can't. That's not true. It's false. Pun intended. White and orange. How do we effectively drop this signal? I guess we just like carry it down like this and then use a target. Right? Let's just call it a target. That's actually so nice. A target was a very Minecraft. If something is in Python is Pythonic, that's very Minecraftian, which is a pretty horrific way of putting it. But I think you get what I mean, where a target makes sense. It would be in the game because there's a bow and it's a silly little block. Look at it. It's a 3D target. It makes no sense. That's such a Minecraft thing to have. Because look, that powers. So if you guys didn't know, with a target block, if you shoot at the target, and the air's on there, it sends out a little tick, a couple tick pulse. That's hilarious. Anyway. That kind of ruins our... How do you drop a signal like that? Can you do that easily? Not with anything I'm aware of. So it's just a little more tricky to power this. Oh, we could use a slab, right? Same concept over here. You know, I can't complain. That works. Yeah, no complaints over here. No complaints. Because if anything, that just makes it more consistent with our design, right? So we'll drop it with this. Pull that over. Dust. Gorgeous. Gorgeous. Absolutely gorgeous. I'm loving that. I'm absolutely loving that. That's even if this is not the most efficient, that's I love it. Okay. Orange and yellow. Let's do it. Let's bring it on, right? Orange and yellow. Okay. It's orange. We can just bring down the same block, right? The same power? Yeah, it's taken from the same signal, so that totally makes sense. Okay. I think we're going to have to slab it again. Oh, but is that yellow? It is. Okay, not as easy or straightforward as I thought. Actually a bit tricky. We only have 2 blocks to work with. How are we going to get that signal out? I guess that was bound to happen. So here's my idea, okay? Please don't have any conflicts. Right? Right? We're bringing it down. Am I right? We're going to keep that the same. We'll just nuke the slab. Right? Oh, see, this is what I love about redstone. It's that little problem solving is so satisfying. Oh, so satisfying. Look at this, everyone. Love it. Love it. Love it. Very passionate about this. That's great. Now, if anyone could tell me what area of computer science this is most concerned with, where I could just do this all day, I'm sold. I can't go back for E, that's too long. I don't want to get a whole degree, but look at this, guys. If anyone can figure that out, seriously, drop down a comment. How do I do this in real life and get paid? I'm kidding. I have an amazing job. It's funny to think about sometimes because this is just so much fun, you know? This is a whole bunch of fun. Oops. That all does something kind of unique. So I think we're on the right track. So what are we doing now? Okay, 3 XORs. That's where it gets funky. So, and they take power from the... Okay. We could do this. It's just getting tricky. So, 2 XORs, right? So let's distribute that. We have 10 blocks here. So if we have 8 and we have the difference, okay. So we need the difference of 2 split down the middle. Okay. What I mean by that is 1, 2, 3, 4. Is that 5? Yeah, knew it. 1, 2, 3, 4. Okay. So the difference of 2 split down the middle. Symmetry. Okay. Let's bring that up. Let's build that out. Be honest, the last few streams were pretty rough for me. Just didn't know how to go forward. I'm having a lot of fun now. I think just trusting the process and trusting that it'll work out and trusting God. Sounds dramatic, but sometimes this stuff can be discouraging, you know? Especially when you're passionate about it and you want to be good at it and you don't really feel like that might be an option for you. Anything is possible with God, right? So let's try this. That's reasonable, don't you guys think? I think that's reasonable. So what are we actually connecting here, right? What's going to be the challenge? So the end of that XOR, which is the only connection it actually has. Great. And then orange. And so the special part here is you really need to make sure that you're powering it from both of these sides, starting from here, because if you power it from the center, it totally messes up this distance logic. And I'm sure you guys can understand why that might be the case. So I think we invert this. so that the redstone's coming out this way. See, the funny part of redstone is I was like, oh, this is just gonna work, and like it'll have the same design every time. No, it won't, because redstone, it's because it's a 3D world and you're building in 3 dimensions. That is X, Y, and Z. It's just hard to know where those conflicts are going to arise in volume. I heard once that humans are not very good at visualizing volume, but they're much better at visualizing distance. So right when you add this 3-dimension, it's just more difficult because it's like you're going up and left and right, and also another left and right. So it's like, it's just different. Here's what I think we do. We're really adding on the time, aren't we? Really adding on the time, because that logic needs to stay the same. So, okay, so now we have orange. We need to connect orange. I think we rip it like this, bring it up. I mean, that to me seems like the only reasonable way to do that. And then we throw a repeater down, right? I think that just makes sense. I mean, does that look better? I think so. I think that does look better. So, great. That looks great. Next. 2 ands are connecting to that XOR. That is the second and third and. These 2 guys are connected. Ooh, okay. So let's get rid of the lamps, give ourselves some space. Let's use white again. I know. Let's use white. Second and third. I think that's the best way we're going to do that. It's getting tough. We might have to go under. And I think you'll see what I mean in just a second. We're going to have to use target blocks. We're going to do this. Not it again. Do that. Okay. How many ticks is this? Is that equivalent to this or this? That's my question. Let's do an experiment. Okay, lovely. Right? Okay. Here's the experiment. If I was to hook this up, in the most jank way I can, and they have exactly the same different. Okay, that's the same. So each redstone torch is 1 tick delay. And that's important. Timing is important, right? At the beginning it's not, but it becomes important. And I think that's very much worth noting. I almost don't want to destroy that. But time, okay, torches represent 1 tick. And you know what? We're going to trek it all the way back. We're going to note that. We could just we should just have some sort of TP. Me when I go camping. Okay. On true 5 volts high. Off volts, 0 volts low. I mean, that's fair enough, right? -0, okay. I mean, I just want to note that this is a delay of 1 tick, right? Let's go back. Let's check out the stream. Okay, we are at 1 hour and 5, right? So we're just coming up on the end. I think we push through and we finish this full ladder. Okay. So we're gonna not worry about timing for this specific application. Oh, look at that. No, wait, I'm sorry. Yeah, that's it. I'm sorry. I just had a false revelation. Guess we could try to equivocate. Equalize, I should say. I don't know. Right. Nice. It's not too bad. Uses the same delay. Like, that's fine. Just maybe not the same delay over there. Actually, definitely not. Now it's all the same. Isn't that nice? Because you have 2 repeaters here, and then 1 repeater at a delay of 2. I like that. Very good. Okay. And then the final XOR, which is connecting the final AND. And so this is just this. Okay, the left side is done. This is going to the sum. So that's the sum right here. Okay, that's done. So as for this, we need XOR again. Connected to the final and the final XOR. So we need to connect. Let's just mark this. This output. No, we need a unique block for that. The classic green terracotta, folks. Terracotta, because that green glaze, excuse me, because that is just a disgusting block. And I will never forget it until it's gone. So we need to connect those to a final XOR. So I think, oh, you know what? You know what, guys? Look at that. Sorry, I'm getting a little aggressive here. It's like cuteness aggression almost, because it's just like, look, it's, this is so good. Now, if we can wire this in a way that's lovely, then we're golden. So what do we have going on? Here's an idea. No, that's the output, isn't it? That's just the connecting to the output. So we want that. And then we still want a repeater there, I think. That's not part of the circuit, so that needs to be white. Disconnect. Great. Makes sense. Just for the sake of continuity. And for the sake of consistency there. Great. We don't need to rip that signal out, so that's going to be the carry. So we need to connect. Oh, sorry, that's already connected. So we have one final. This is like the, oh, I did not know you could toggle that. That's genius. Because there was a whole debate, like, should this be the default or this? That's lovely. And yeah, just want to admonish the developers for that, because wow. Okay. We need to connect. It's actually a bit tricky because this is the hardest one. I mean, maybe not if we brought this up, right? We're going to need a separator block here, which is totally agreeable with the design. This is going to be the worst part, I would say, in terms of how concise it is, because we do have to kind of break this whole equilibrium, the wiring. I think we bring that one more because we can't drop that, or can we? I think we do. I think we drop that because if we can improve our design, then we drop it. The carry is in a bit of an awkward space, and that will get powered too. We're really taking this to the next level of modifying our gates just to make this work. Is that actually too far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, see, here's the kicker is we need to do that. So it doesn't actually matter anyway. But here's what we're going to do. Boom. How do you like that? Okay, beautiful. Yeah, not so much. I mean, it's not the most beautiful part of the design. How do we lower as much of this as we can without interfering with the rest of the signal? No. When you don't have to do a separator block, you shouldn't. Okay, I mean, there we have it, right? I think that's reasonable. So we have, let's just rip these signs, guys. Don't do the same thing twice. Sum and carry. And if you want to know how I just copied the metadata of these signs, or I guess the content, is I did Control, Shift, and middle click, or the third button on the mouse. Okay. Moment of truth. Do we have a truth? Do we have a full adder? So I guess we should illustrate this truth table. So let's just verify, right, before we build that truth table. And when everything's off, both the desired carries on, right? Obvious. When input 1 is on, just the desired sum of 1 is on. Good. Third column. Remember, columns vertical, rows horizontal. Columns vertical, rows horizontal. You can remember this is rows if when you're rowing a boat, it's an entirely horizontal task. Columns, if you think of like Roman columns or something, vertical, or the columns that support a federal building, they're vertical, okay? Vertical, columns, horizontal, rows. So third column, and just for the sake of illustration, third column, 1, 2, 3, fourth row. We're concerned with that output. So actually we're concerned with the second row of input, right? So anyway, I digress. Input 2 should be on, and then the desired sum is on. Great. I think that's the same with 3. Great. That all makes sense. Input 3, when 1 and 2 are on, the carry should be on, but the sum should be off. This is very exciting. Okay. Right, that tracks. When just input 3, yep, that's a sum. We already tracked that. 1 and 3 should be a desired carry of 1. And if you guys didn't know, 1, 2, 3, we're sending here. Carry of 1, sum of 0, right? When 2 and 3, it's a same thing. Same thing, great. And then when all of them are on, both should be on. 3 inputs, 2. Guys, what a lovely way to end the episode. Honestly, I've had a fantastic time. Let's flesh this out as always. We always give a 1 block space gap around the perimeter to highlight the cohesiveness, but the levers don't apply. That's just my mental model because they're not really a block. That's the full adder episode in Turing Complete, ladies and gentlemen. I am very proud about that. Okay, we don't have to, because we're dragging this episode on a little bit. We're just about 15 minutes over. I'll do the truth table off camera because you guys already know how I do truth tables, okay? Thank you all for watching. Thank you for tuning in. We had a couple of live commenters in the chat, and that was awesome. Great to see. Yeah, thank you guys for another great episode. It was a little rough these last couple ones, but I think we really turned it around here, and this is really exciting. We did a full adder, guys. We can add into a byte. I mean, that's like clear progress. I honestly think that we might be able to use that as the signal counter to go back and to do counting signals. Well, not just that. Yeah, I think this looks great. I think this is one of my best looking ones. It's still a bit of spaghetti. It's like the spaghetti code equivalent of whatever you would call this circuit design, and the timing is equivalent. It's just, yeah, it's lovely. I was very satisfied. There's color coding. I think the buses, I think we're going to move forward. I think we're going to keep using this bus strategy because it was incredibly fruitful this time around. Incredibly fruitful. And all the color coding just really helps you see what's going on here, right? And yeah, who doesn't love slabs? Okay. I'm going to close this off. I never know exactly how to close these off. Thank you for watching. Tune in next time. We're going to be moving on to the double the number level. We completed full adder. We're making our way up, and eventually we're going to achieve Turing Complete. Okay. Catch you on the next one. Take care.